Hello, in this lecture we'll answer two questions. In the first question, we'll find out the area of this circle, and in the second question, we'll find out the area of trapezoid ABCD. Okay, so we'll start with the first question. In the drawing, we have a circle, and we have also the right triangle ACP that cuts the circle at 2 points, A and this point. We know that side CP of the right triangle ACP equals to 4 units in its length. This is side BC, that is equals to 1 unit. And our mission is to find out the area of this circle. So first of all, we can implement rule 2, because if we focus on this common external point P, from this common external point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. So write it down. So, according to rule 2, the length of tangent PA must be equal to the length of tangent PB. But actually, it is given us the question that PB in total equals to 4 plus 1, that is 5. So we can write here that PB equals to 5. And from this equation, PA equals to PB equals to 5. We will derive that PA also equals to 5 units in its length. PA equals to 5. So this is side PA, that is equals to 5 units in its length. In the next step, I'll copy the right triangle ACP in a new page, and we will implement the Pythagoras theorem of this right triangle, triangle ACP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a proposition from Pythagoras theorem. So actually, this is the right triangle ACP that is coming from the original drawing. According to the Pythagoras theorem, in this right triangle ACP, AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. So write it down. AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. AP equals to 5 units in its length, therefore AP squared is 5 squared, that is 25, and it is equals to AC squared. AC is the missing side, so we leave it as it is. So it is AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total we should find out that 25 equals to AC squared plus 16. Here we will subtract 16 from this equation, and we get that 25 from 16 is 9, so 9 equals to AC squared. Here we take a root out of this equation, and finally we get that AC equals to the square root of 9, that is 3. So we found out that the missing side AC equals to 3 units in its length. So here AC equals to 3 units in its length. So I write it down. Here AC equals to 3 units in its length. we know that according to what is given as a question, PA and PB are two tangents to this circle at points A and B. So PB is a tangent. PB is a tangent, it is absolutely a straight line. PB is a tangent, it is absolutely a straight line. So if we focus on the upper side of the straight line PB at this point C, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of PB at point C? We have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we'll define the center of this circle. This point is point O. And we will join points O and B together by a straight line. We will also define the radius of this circle as x. What is the definition of line segment OB? Line segment OB starts from point O, that is the center of the circle, and then at point B, that is the point of the circle itself. This is exactly the definition of a radius. Therefore, OB is the radius of this circle, and it is equal to x according to our definition. So OB equals to x. Here we can implement rule 1. Why? Because we have the radius OB that is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. In the next step, we will do a construction, that is to say, from the center of this circle, that is to say, from this point O, we will draw perpendicular on AC. Again, from point O, we will draw perpendicular on AC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O and AC. This point is point E. Actually, by doing this construction, we created the right quadrilateral OECB. Inside quadrilateral OECB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OECB, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate quadrilateral OEBC is a rectangle because it has 4 right angles. So write it down. Quadrilateral OEBC is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in a rectangle OECB, side BC must be equal to the opposite side OE. But BC is 1, therefore OE must be also equal to 1 unit in its length. Likewise, according to the same rule, in the same rectangle OECB, side OB must be equal to the opposite side EC, but OB is x, therefore EC must be also equal to x units in its length. What is the length of line segment AE? From the drawing, it is very easy to see that AE equals to AC minus EC. Again, AC minus EC equals to AE. So I write it down. AE equals to AC minus EC. So AE equals to AC. We already found out that AC equals to 3 units in its length minus EC. EC equals to x. So in total, we actually found out that A equals to 3 minus x units in its length. A equals to 4 minus x units in its length. In the next step, we join points O and A together by a straight line. What is the definition of line segment OA? Line segment OA starts from point O, that is the center of the circle, and then at point A, that is the point on the circle itself. So this is exactly the definition of a radius. Therefore, OA is the radius of this circle, that is equal to x. In the next step, I'll copy the right green triangle OAE in a new page, and we will implement the Pythagoras theorem on this right green triangle OAE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the version for Pythagoras theorem. So actually, this is the right green triangle OAE that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle AOE, AO squared, that is the square of the hypotenuse, equals to AE squared plus OE squared. So write it down. AO squared, that is the square of the hypotenuse, equals to AE squared plus OE squared. The hypotenuse AO equals to x units in its length, therefore AO squared equals to x squared, and it is equals to AE squared. AE is 1, therefore AE squared is 1 squared, that is 1, plus OE squared. Actually, OE is 1, therefore OE squared is 1 squared, that is 1, plus AE squared. AE is 3 minus x, therefore AE squared is 3 minus x squared. So in total, we actually found out that x squared equals to 1 plus 3 minus x squared. Here we'll open the brackets on this side of the equation, and finally we get that x squared equals to 1 plus 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared, minus 2 times 3 times x, that is minus 6x. So here we have x squared on both sides of the equation, so x squared will get cancelled. So we cancel x squared, in this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 1 plus 9, that is 10, minus 6x. So we found out that 0 equals to 10 minus 6x. Here we add 6x to this equation, and finally we get that 6x equals to 10. Here we divide this equation by 2, and finally we get that 6x over 2 is 3x, equals to 10 over 2 is 5. So 3x equals to 5. Here we divide this equation by 3, and finally we get x, that is the radius of the circle, x equals to 5 over 3 units in its length. Our mission is to find out the area of this circle. The area of any circle equals to pi times the radius of the circle squared. Pi times the radius of the circle squared. And therefore the area of our circle must be equal to pi. The radius of this circle is x, the radius squared is x squared. So the area of our circle equals to pi x squared. So it is pi, and just right now found out that x equals to 5 over 3. If x equals to 5 over 3, it means that x squared must be equal to 5 over 3 squared. So in total we shall find out that the area of this circle equals to pi times 5 over 3 squared. That is to say, it is pi times 5 over 3 squared. 5 over 3 squared equals to 5 squared, that is 25, over 3 squared, that is 9. So in total we shall find out that the area of this circle equals to either 25 pi over 9 square units, so in terms of numbers, the area of this circle is equals to 8.727 square units. Repeat again, we shall find out that the area of this circle equals to either 25 pi over 9 square units, so in terms of numbers, the area of this circle equals to 8.727 square units. So we finished with the first question. In the next step, I present to you the second question, and we'll solve it. So, in the second question, our mission is to find out the area of this trapezoid ABCD. The area of any trapezoid equals to the sum of its two parallel bases times the height over 2. So I write it down. The area of any trapezoid is equals to the sum of the two parallel bases. In our specific trapezoid, the two parallel bases are AB and DC. And the sum of the two parallel bases is AB plus DC, of course. So the sum of the two parallel bases is AB plus DC times the height. We define the height as h, abbreviation for height. And the height, h, must create 90 degrees with the two parallel bases. That is to say, it must create 90 degrees with the base AB, and it also must create 90 degrees with the base DC. So in conclusion, we shall find out that the area of trapezoid ABCD equals to the sum of its two parallel bases, that is AB plus DC, times the height over 2. And the height must create 90 degrees with the two bases AB and DC. In the next step, we will do a construction, that is to say, from this point A, we will draw perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point A in DC. This point is point E. We will define this line 70 as x. And we will also define the line segment of side AE. Actually, side AE is also the height of trapezoid ABCD. Why? Because side AE creates 90 degrees with the base DC, and therefore AE must be the height of trapezoid ABCD. So we define side AE as h because it is the height of trapezoid ABCD. So AE equals to h units in itself according to our definition. So by doing this construction, we created the right triangle AED. So copy the right triangle AED in a new page, and we will implement the Pythagoras theorem of this right triangle, triangle AED. Here by PT is the equation for Pythagoras theorem. So assuming this is the right triangle AED that the comes from the original domain, according to the Pythagoras theorem, this right triangle AED, AD squared, that is the square of the hypotenuse, equals to AE squared plus DE squared, plus DE squared. So I'll write it down. AD squared, that is the square of the hypotenuse, this will be equation 1, equals to AE squared plus DE squared. AD is 17, therefore AD squared is 17 squared, that is 289, and it is equals to AE squared. AE is 8, therefore E squared is 8 squared, plus DE squared. DE is x, therefore DE squared is x squared. So in total we should find out that according to equation 1, h squared plus x squared equals to 289. In the next step, we will do another construction, that is to say, from this point B, we will do, from this point B, we will do perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point B in DC. This point is point F. Actually, those two angles, they are both equal to 90 degrees according to our construction. We know that side AB is parallel to side DC because ABCD is a trapezoid. So we know that side AB is parallel to side DC. And this angle equals to 90 degrees. Those two angles, they are located between the parallel lines AB and DC. And therefore, those both angles are defined as the interior angles. And those two angles, they are both located from the right side of the straight line BF, and therefore they are also defined as one-sided angles. So those two angles, they are simultaneously one-sided angles and also interior angles. And according to rule 16, the sum of two one-sided and interior angles is equal to 180 degrees. So the sum of those two angles, according to rule 16, is equal to 180 degrees. This angle equals to 90 degrees. Therefore, this missing angle must be equal to 90 degrees in its size. In order to complete the sum of those two angles to 180 degrees, this angle must be equal to 90 degrees in its size. So actually, this angle equals to 90 degrees according to rule 16. Likewise, we have the same situation here. Those two angles, they are both located between the parallel lines AB and DC, and therefore they are defined as an interior angles. And those two angles, they are both located from the left side of the straight line AE. And for that reason, they are defined as also one-sided angles. So those two angles, they are both defined as one-sided and interior angles, and according to rule 16, the sum of two one-sided and interior angles is equal to 180 degrees. But this angle equals to 90 degrees, therefore this missing angle must be equal to 90 degrees in its size. when those two angles are both equal to 90 degrees according to rule 16. So we actually found out that inside quadrilateral ABFE we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a right angle if not a square. So we relate quadrilateral ABFE is right angle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in a rectangle ABFE, side AB must be equal to the opposite side FE. But AB is 16, therefore FE must be also equal to 16 units in its length. Likewise, according to the same rule, in the same rectangle ABFE, side AE must be equal to the opposite side BF. But AE equals to 8 units in its length according to our definition. Therefore, BF must be also equal to 8 units. So in the next step, I'll copy the right triangle BFC in the new page and we'll implement the Pythagoras theorem on this right triangle BFC, but before that, we'll find out what is the length of side FC. From the domain, it is very easy to see that FC equals to DC minus DE minus EF. Again, FE in total equals to DC minus DE minus DF. So I write it down. The missing side FC is equals to DC minus DE minus EF. So in total FC equals to DC. DC equals to 44 units in its length according to what is given as the question, minus DE. DE equals to X according to our definition, minus EF. We just right now found out that EF equals to 16 units in its length. So it is minus 16. So in total FC equals to 44 minus 16 is 28 minus X. So we found out that side FC equals to 28 minus X units in its length. So in the next step, I copy the right triangle BFC in a new page and we will implement the Pythagoras theorem in this right triangle BFC. The hypotenuse BC of the right triangle BFC equals to 25 units in its length according to what is given as the question. We just right now found out that FC equals to 28 minus X units in its length and BF equals to 8 units in its length according to what we already found out. Here by PT is a version for Pythagoras theorem. So actually, this is the right triangle BFC that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle BFC, BC squared, that is the square of the hypotenuse, equals to BF squared plus FC squared. So I write it down. BC squared, that is the square of the hypotenuse, equals to BF squared plus FC squared. BC is 25, therefore BC squared is 25 squared, that is 625, and it is equals to BF squared. BF is 8, therefore BF squared is 8 squared plus FC squared. FC is 28 minus X, therefore FC squared is 28 minus X squared. So in total we should find out that 625 equals to 8 squared plus 28 plus X squared. We will open the brackets on this side of the equation and finally get that $625 equals to 8 squared plus 28 minus x squared. 28 minus x squared equals to 28 squared, that is 784 plus x squared minus 2 times 28 times x is minus 56x. Here we subtract 625 from this equation, equation 2. So in this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have h squared plus x squared, and 784 minus 625 equals to 159 minus 56x. Here we get 56x from this equation, equation 2. And finally we get that according to this equation, equation 2, 56x equals to h squared plus x squared plus 159. We have already found out that this expression h squared plus x squared, according to equation 1, is equals to 289. Therefore, I can substitute x squared plus x squared in this equation 2 by 289. We'll do it now, we get that according to equation 2, 56x equals to x squared plus x squared according to equation 1 is 289 plus 159. So in total, we should find out that according to equation 2, 56x equals to 289 plus 159, it is equal to 448. So here we divide this equation, equation 2 by 56, and finally we get that x, that is, let me see red, x is, let me see 970e, is equals to 448 over 60 over 56, it is equals to 8. So if you found out that the length of 970e, x is equals to 8 units. Okay? So, we already found out that according to equation 1, according to equation 1, we have already found out that h squared plus x squared equals to 289. We just right now found out that x equals to 8. If x equals to 8, it means that x squared equals to 64. Now we can substitute x squared in this equation, equation 1 by 64. We'll do it now, and we get that according to this equation, equation 1, h squared plus x squared, that is 64, equals to 289. Here we subtract 64 from this equation, equation 1, and finally we get that according to equation 1, h squared equals to 289 minus 64 is equals to 225. So in total, we found out that according to equation 1, h squared equals to 225. Here we take a root for this equation, equation 1, and we get that the height edge of the quarter circle equals to the square root of 225, that is 15. So we found out that the height of this trapezoid ABCD edge equals to 15 units in its length. Our mission is to find out the area of this trapezoid ABCD. So what is the area of trapezoid ABCD? The area of trapezoid ABCD is equals to the sum of its two parallel bases, that is actually AB plus DC, times the height, that is h, divided by 2. So the area of trapezoid ABCD in total will be equal to AB 16, plus DC is 44, times the height h, we just find Right now found out that the right edge is equals to 15, so it is times edge, that is times 15 divided by 2. So in total we should found out that the area of trapezoid ABCD equals to 16 plus 44 is 60 over 2 times 15. 60 over 2 is 30 times 15. So if we found out that the area of trapezoid ABCD equals to 30 times 15, that is 450 square units. So the area of trapezoid ABCD is equals to 450 square units. If it again, we should found out that the area of this trapezoid ABCD is equals to 450 square units. In the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our mission was to find out the area of this circle. So in the drawing, we have a circle and also the right triangle ACP. The right triangle ACP cuts the circle at 2 points, A and this point. We know that side CP of the right triangle ACP equals to 4 units in its length. This is an angle ACP, that is the right angle. And line 7 CB equals to 1 unit in its length. Again, our mission is to find out the area of this circle. So first of all, we can implement rule 2 in our drawing. Why? Because in our drawing, we have the common extreme point P. For this common extreme point P, we have two tangents to this circle. Tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. It's given us the question that PA and PB are the two tangents to this circle. And according to rule 2, the length of tangent PA is equal to the length of tangent PB. According to rule 2. But according to what is given as the question, PB in total equals to 4 plus 1, that is 5. So here, we know that PB equals to 5. And from this equation, PA equals to PB equals to 5, we will derive that PA equals also to 5 units in its length. This is side PA that is equals to 5 units in its length. In the next step, I copied the right triangle ACP in a new page and we implemented the Pythagoras theorem of this right triangle ACP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. This is the right triangle ACP that I copied from the original drawing. According to the Pythagoras theorem, this right triangle ACP, AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. AP is 5, therefore AP squared is 5 squared, that is 25, and it is equals to AC squared. AC is the missing side, so we will leave it as it is, plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total, we should find out that 25 equals to AC squared plus 16. Here we subtracted 16 from this equation, and finally found out that AC squared equals to 25 from 16 is 9. So AC squared equals to 9. Here we took a root out of this equation, and finally found out that AC, the missing sign AC, is equals to the square root of 9, that is 3. So AC equals to 3 units in its length. So we can write here that AC equals to 3 units in its length. This is line 7 AC, that is equals to 3 units in its length. In the next step, we defined the center of this circle. This point is point O. And we also defined the radius of this circle as x. Then we join points O and B together by a straight line. What is the definition of line 7 to OB? Line 7 to OB starts from point O, that is the center of the circle, and that's at point B, that is a point on the circle itself. So this is exactly the definition of a radius. Therefore, OB is the radius of the circle, that is equal to x according to our definition. So here we can implement rule 1 because we have the radius OB that is equal to x. The radius OB is drawn to point B, that is the point of tendency PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees, according to rule 1, of course. We know that PB is a tangent to this circle, and this point B. So PB is a tangent, it is absolutely a straight line. So if you focus on this straight line P, on the upper side of the straight line PB, at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line PB at point C? We have this angle that is the right angle according to what is given in the equation, plus this missing angle. In total they must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step we joined points O. We did a construction, that is to say from the center of the circle, that is to say from this point O, we draw perpendicular on AC. Again from point O we draw perpendicular on AC. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. By doing this construction we created quadrilateral OECB. Inside quadrilateral OECB we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OECB we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle if not a square. So we relate to quadrilateral OECB as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OECB, side OE must be equal to the opposite side BC. But BC equals to 1, therefore the opposite side OE must be also equal to 1. Likewise, according to the same rule, in the same rectangle OECB, side OB must be equal to the opposite side EC. But OB is x, therefore the opposite side EC must be also equal to x. What is the length of the missing line segment AE? From the drawing it is very easy to see that AE equals to AC minus EC. Again, AE equals to AC minus EC. Here, AE equals to AC minus EC. So AE equals to AC, AC is 3, minus EC, EC is x. So in total, AE equals to 3 minus x units in its length. In the next step, we join points O and A together by straight line. What is the definition of line segment OA? Line segment OA starts from point O, that is the center of the circle, and ends at point starts from point O, that is the center of the circle, and ends at point A, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore, O is the radius of the circle, that is equal to x according to our definition. In the next step, I copy the right hand triangle OAE in a new page, and we implemented the Pythagoras rule on this right hand triangle OAE. So actually, this is the right hand triangle OAE that I copied from the original drawing. According to the Pythagoras theorem, this right triangle OAE, AO squared, that is the square of the hypotenuse, equals to AE squared plus EO squared. Again, AO squared equals to AE squared plus OE squared. AO is x, therefore AO squared is x squared, and it is equals to AE squared. AE is 3 minus x, therefore AE squared is 3 minus x squared, plus OE squared. OE is 1, therefore OE squared is 1 squared, that is 1. So in total we should find out that x squared equals to 1 plus 3 minus x squared. Here we open the brackets on this side of the equation and finally found out that x squared equals to 1 plus 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared minus 2 times 3 times x, that is minus 6x. So here we have x squared on both sides of the equation, so x squared will get cancelled. So we cancel x squared, on this side of the equation we left with nothing, that is to say 0. On the other side, other in the equation we have 1 plus 9, that is 10, minus 6x. In conclusion, we should have found out that 0 equals to 10 minus 6x. Here we added 6x from this equation and finally found out that 6x equals to 10. Here we divided this equation by 2 and finally found out that 6x over 2 is 3x and 10 over 2 is 5. So in total we should have found out that 3x equals to 5. Here we divided this equation by 3 and finally found out that x equals to 5 over 3 units in its length. That is to say, the radius of this circle x equals to 5 over 3 units in its length. Our mission is to find out the area of this circle. The area of any circle equals to pi times the radius of the circle squared. Okay, again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of this circle, that is x squared. That's actually pi x squared. The area of our circle equals to pi x squared. But we have already found out, just right now found out, that x equals to 5 over 3. If x equals to 5 over 3, it means that x squared must be equal to 5 over 3 squared. So in total, if we found out the area of the circle equals to 5 times 5, pi times 5 over 3 squared. So it is pi, and 5 over 3 squared equals to 5 squared, that is 25 over 3 squared, that is 9. So in total, we actually found out that the area of this circle equals to either 25 pi over 9 square units, or in terms of numbers, the area of this circle equals to 8.727 square units. So we finished with the first question. In the next step, I presented to you the second question, and we solved it. Our mission in the second question is to find out the area of this trapezoid. Our mission in the second question is to find out the area of this trapezoid ABCD. Actually, we know that the area of any trapezoid equals to the sum of its two parallel bases. That is, in this case, it is AB plus DC times the height, that is h, divided by 2. And the height h must create 90 degrees with the two bases. That is say with AB and DC. Okay, again, the area of trapezoid ABCD will be equal to the sum of its two parallel bases, that is actually AB plus DC, times the height, that is h, and the height h must create 90 degrees with the two bases AB and DC divided by 2. So in total, the area of trapezoid ABCD must be equal to AB plus DC, that is the sum of the two bases, times the height h over 2. Okay, so in the next step, we did a construction, that is to say, from this point A, we draw perpendicular on DC. Again, from point A, we draw perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in DC. This point is point E. We define the length of line 7DE is x, and we define the length of AE is h. AE creates 90 degrees with the base DC, and therefore AE is the height of trapezoid ABCD. So A equals to h, that is the height of trapezoid ABCD. So in the next step, I covered the right triangle AD in the new page, and we implemented the Pythagoras theorem in the right triangle AD. Okay, this is the right triangle AD that I covered from the original drawing. According to the Pythagoras theorem, this right triangle AD squared, that is the square of the hypotenuse, equals to AE squared plus DC squared. AD is 17, therefore AD squared is 17 squared, that is 289, and it is equals to AE squared. AE is h, therefore AE squared is h squared, plus DE squared. DE is x, therefore DE squared is x squared. So, in conclusion, we found out that according to equation 1, 289 equals to h squared plus x squared. In the next step, we did a second construction, that is to say, from this point B, we drew perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B in DC. This point is point F. So actually, those two angles are both equal to 90 degrees according to construction. Okay, and we know that sine AB is parallel to sine DC, and those two angles are both equal to 90 degrees. Those two angles, they are both located between the parallel lines AB and DC, and therefore they are defined as interior angles. But those two angles, they are also located from the right side of the straight line BF, and therefore they are also defined as one-sided angles. So in total, those two angles are defined as interior and one-sided angles. And according to rule 16, the sum of two interior and one-sided angles is equal to 180 degrees. So the sum of those two angles, according to rule 16, must be equal to 180 degrees. But this angle equals to 90 degrees according to our construction, and therefore this missing angle must be equal to 90 degrees in its size. Again, in order to complete the sum of those two angles to 180 degrees, this missing angle must be equal to 90 degrees in its size, according to rule 16, of course. Likewise, those two angles are also defined as one-sided and interior angles. For the same reasons, that those two angles are also defined as one-sided and interior angles. Well, because those two angles are both located between the parallels AB and DC, and they are both located on the right side, on the left side of the straight line AE. And therefore, in total, those two angles are defined as interior and one-sided angles. And according to rule 16, the sum of two interior and one-sided angles is equal to 180 degrees. That is to say, the sum of those two angles must be equal to 180 degrees according to rule 16. This angle equals to 90 degrees according to our construction, and therefore this missing angle must be also equal to 90 degrees in its size. So, actually, we found out that inside quadrilateral ABFE we have four right angles. But according to rule 5, any quadrilateral that has four right angles must be a rectangle if not a square. So we relate to quadrilateral ABFE as a rectangle because it has four right angles. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle ABFE, side AB must be equal to the opposite side EF. But AB 16, therefore EF must be also equal to 16 units in its length. Likewise, according to the same rule, in the same rectangle ABFE, side AE must be equal to the opposite side BF. But AE is edge, therefore BF must be also equal to edge. What is the length of the missing side FC? From the drawing it is very easy to see that FC equals to, in total, to DC minus DE minus EF. Again, FC in total equals to DC minus DE minus EF. Again, FC equals to DC minus DE minus EF. So FC in total equals to DC, that is 44 according to what is given as the question, minus DE, that is X according to our definition, minus EF, that is 16. So in total, FC equals to 44 minus 16, that is 28 minus X. So in total, FC equals to 28 minus X units in its length. In the next step, I copied the right triangle BFC in a new page and we implemented the Pythagoras theorem in the right triangle BFC. So actually, this is the right triangle BFC that I copied from the original domain according to the Pythagoras theorem, and this right triangle BFC, BC squared, that is the square of the hypotenuse, equals to BF squared plus BC squared. BC is 25, therefore BC squared is 25 squared, that is 625, and it is equals to BF squared. BF is 8, therefore BF squared is 8 squared, plus FC squared. FC is 28 minus X, therefore FC squared is 28 minus X squared. So in total, we have found out that according to equation 2, 625 equals to 8 squared plus 28 minus X squared. Here we open the brackets of this side of equation 2, and finally found out that according to this equation 2, 625 equals to 8 squared, and 28 minus X squared equals to 28 squared, that is 784, plus X squared minus 2 times 28 times X, that is minus 56X. Here, we subtracted 625 from this equation, so this side of the equation we left with nothing, that is to say 0. On the other side of the equation, we have X squared plus X squared, and 789 minus 625 equals to 159 minus 56. So in total, according to equation 2, we have found out that 0 equals to X squared plus X squared plus 159 minus 56X. But according to equation 1, we have already found out that X squared plus X squared equals to 289. Therefore, we can substitute X squared plus X squared in this equation 2 by 289. We did it, and we actually found out that, again, X squared, but before that, actually, we subtracted 56X from this equation, and actually found out that 0 plus 56X is 56X, and it is equal to X squared plus X squared plus 159. Now we actually substitute h squared plus x squared by 289. Actually found out that according to this equation in equation 2, 56x equals to h squared plus x squared, that is 289 plus 159. So 56x equals in total to 289 plus 159. 289 plus 159 equals to 448. So in total we found out that according to equation 2, 56x equals to 448. Here we divided this equation 2 by 56 and finally found out that the missing line segment x is equals to 448 over 56, this is 8. So x equals to 8 units in itself. This is 978, it is equals to x, and it is equals to 8 units in itself. Okay. Now, according to equation 1, we already found out that h squared plus x squared equals to 289. We just right now found out that x equals to 8. If x equals to 8, it means that x squared must be equal to 8 squared, that is 64. Therefore, we can substitute x squared in this equation 1 by 64. We did it and found out actually that according to equation 1, h squared plus x squared, that is 64, equals to 289. So according to equation 1, we actually found out that h squared plus 64 equals to 289. Here we subtracted 64 from this equation 1, and finally found out that according to this equation 1, h squared equals to 289 minus 64 is 225. So in total we found out that according to equation 1, h squared equals to 225. Here we took a root out of this equation and finally found out that h, that is the height of trapezoid ABCD, equals to the square root of 25, that is 15. So the height of this trapezoid ABCD, h equals to 15 units. Our mission is to find out the area of this trapezoid ABCD. The area of trapezoid ABCD equals to the sum of its two parallel bases, that is to say it is AB plus DC times the height h over 2. Okay, again, the area of trapezoid ABCD in total is equals to the sum of its two parallel bases, that is AB plus DC times the height h over 2. AB is 16, DC is 44, times the height h is 15 divided by 2. So in total, the area of trapezoid ABCD equals to 16 plus 44, that is 60, divided by 2 times 15. 60 over 2 is 30. So in total, the area of trapezoid ABCD equals to 30 times 15, that is 450. So we found out that the area of this trapezoid ABCD is equals to 450 square units. Okay, thank you very much.